Unveiling the secrets of the universe. Physical quantities. The universe is a vast and mysterious place, but hidden within its intricate tapestry are patterns and laws that govern its every move. Physics is the key to unlocking these secrets. It allows us to understand the fundamental principles that govern everything from the smallest atom to the largest galaxy. At the heart of physics lies the concept of physical quantities. These are properties of matter, energy, or phenomena that can be measured. Think of length, mass, time, temperature, or electric current. Each of these quantities plays a crucial role in describing the world around us. Without physical quantities, our understanding of the universe would be purely qualitative. We could describe the color of the sky or the feeling of warmth from the sun, but we wouldn't be able to quantify these observations. We wouldn't be able to say how far away a star is or how much energy it emits. Fundamental versus derived units, building blocks of measurement. To measure physical quantities, we need units. A unit is a standard amount of a physical quantity. For example, the meter is a unit of length, and the kilogram is a unit of mass. Units can be classified into two main categories: fundamental and derived. Fundamental units are the basic building blocks of measurement. They are defined independently of other units. The meter, kilogram, and second are examples of fundamental units. Derived units, on the other hand, are combinations of fundamental units. They are used to express physical quantities that are not directly measured in terms of fundamental units. For example, speed is a derived unit, defined as distance traveled per unit of time. Its unit is meters per second, a combination of the fundamental units of length, meter, and time, second. The distinction between fundamental and derived units is important because it highlights the interconnectedness of physical quantities. It shows how complex concepts can be broken down into simpler, more fundamental ones. The Symphony of SI Units, a universal language. Imagine a world where every country spoke a different language. Communication would be chaotic. Fortunately, in science, we have a universal language, the International System of Units, or SI. The SI system is a globally agreed-upon system of measurement. The SI system is based on 7 fundamental units: meter, the unit of length; kilogram, the unit of mass; second, the unit of time; ampere, the unit of electric current; Kelvin, the unit of thermodynamic temperature; mole, the unit of amount of substance; candela, the unit of luminous intensity. These 7 fundamental units form the foundation of the SI system. Decoding dimensions. Unveiling the nature of physical quantities. Imagine trying to build a house without knowing length, width, and height. Impossible. In physics, understanding dimensions is crucial. Dimensions tell us the nature of physical quantities. They relate to mass, length, and time. Speed, for example, is length over time. Dimensions use square brackets. Length is L, mass is m, and time is t. Derived quantities combine these dimensions. Force, for example, is mLT circumflex 2, derived from Newton's second law. Understanding dimensions has practical applications in both physics and engineering. Section 5. Dimensions in action. Mechanics and heat. In the realm of mechanics, dimensions play a crucial role in analyzing motion, forces, and energy. For instance, the dimension of velocity, which is length per time, tells us that it is the rate of change of position with respect to time. Similarly, the dimension of acceleration, which is length per time squared, indicates that it is the rate of change of velocity with respect to time. Dimensions are also essential in the study of heat and thermodynamics. The dimension of temperature is a fundamental dimension in this field. Other quantities, such as heat capacity, have dimensions that are combinations of fundamental dimensions, including temperature. By understanding the dimensions of physical quantities, we can derive equations, check the consistency of units in our calculations, and gain a deeper insight into the relationships between different physical phenomena. Section 6. Dimensional analysis. A powerful tool for problem solving. Imagine you're faced with a complex physics problem involving multiple variables and equations. How do you even begin to solve it? This is where dimensional analysis comes in. Dimensional analysis is a powerful technique that uses the dimensions of physical quantities to solve problems. It's based on the principle of dimensional homogeneity, which states that the dimensions of each term in a valid equation must be the same. Here are some applications of dimensional analysis: checking the correctness of equations, deriving equations, and converting units. If the dimensions on both sides of an equation are not the same, the equation is incorrect. Dimensional analysis can be used to derive equations that relate different physical quantities. It also provides a systematic way to convert units from one system to another. Dimensional analysis is a valuable tool for physicists and engineers, allowing them to solve problems efficiently and effectively. Section 7. The limits of dimensional analysis, where intuition takes over. While dimensional analysis is a powerful tool, it's important to remember that it has its limitations. It cannot tell us everything about a physical system. Here are some limitations of dimensional analysis. It cannot determine dimensionless constants such as pi or e. It cannot determine the exact form of an equation, and it cannot be applied to equations with trigonometric, logarithmic, or exponential functions. Dimensional analysis can only provide the general form of an equation. It cannot determine the exact mathematical relationship between variables. Despite its limitations, dimensional analysis remains a valuable tool for problem solving in physics. It provides a framework for understanding the relationships between physical quantities and can often lead to insights that would not be obvious otherwise. Section 8. Precision in measurement, significant figures and rounding off. In science, precision is paramount. Measurements are approximations, limited by our instruments. Significant figures ensure meaningful and reliable measurements. They include all known digits plus one estimated digit. For example, 2.54 centimeters has 3 significant figures. Rounding off reduces digits while maintaining value. The rules depend on context and desired precision. Section 9. Maintaining accuracy, significant figures in calculations. When performing calculations with measured quantities, it's crucial to maintain the correct number of significant figures to avoid overstating the precision of our results. Here are the rules for determining significant figures in calculations. Multiplication and division. The result should have the same number of significant figures as the measurement with the fewest significant figures. Addition and subtraction. The result should have the same number of decimal places as the measurement with the fewest decimal places. By following these rules, we can ensure that our calculations are consistent with the precision of our measurements and that our results are not misleadingly precise. Section 10. Orders of magnitude. Grasping the vastness of the universe, from the smallest subatomic particles to the largest galaxies, the universe spans an incredible range of scales. To make sense of these vast differences in size, we use orders of magnitude. An order of magnitude is a power of 10. Each order of magnitude represents a 10-fold increase or decrease in size. For example, the diameter of an atom is on the order of 10 to the minus 10 meters, while the diameter of the Milky Way galaxy is on the order of 10 to the 21st meters. These two objects differ in size by 31 orders of magnitude. Orders of magnitude provide a convenient way to compare the relative sizes of objects and to appreciate the vastness and diversity of the universe. Section 11. Embracing uncertainty, measurement errors and their propagation. In the pursuit of scientific knowledge, we must embrace uncertainty. Every measurement we make is subject to error, no matter how careful we are. Understanding the sources of error and how they propagate through calculations is essential for interpreting our results accurately. Measurement errors can be classified into two main types: systematic errors. These errors are consistent and repeatable, often arising from flaws in the measuring instrument or the experimental setup. Random errors. These errors are unpredictable and fluctuate randomly, often due to environmental factors or limitations in our ability to read instruments. When multiple measurements are combined in a calculation, errors propagate, meaning that the uncertainty in the final result is affected by the uncertainties in each individual measurement. The way errors propagate depends on the mathematical operations involved. By understanding measurement errors and their propagation, we can quantify the uncertainty in our results and present our findings with appropriate caveats and limitations. Section 12. Mastering physics. The significance of understanding measurement. Measurement is the foundation of physics. Without the ability to quantify the physical world, our understanding of the universe would be limited to qualitative observations. By mastering the concepts of physical quantities, units, dimensions, significant figures, and error analysis, we gain the tools we need to explore the universe with precision and accuracy. From the smallest subatomic particles to the largest galaxies, the laws of physics govern the behavior of everything in the cosmos. By understanding these laws and the tools we use to study them, we unlock the secrets of the universe and gain a deeper appreciation for the intricate workings of the natural world.